Good morning, everyone, and welcome to Stream 3 at DSC MENA 2025. I'm Yusuf. I will be your host for today, and we are kicking things off with truly cutting-edge session. Please welcome Mr. Sameh Zaghloul, CTIO at Fitz Solutions, who will explore how quantum computing and generative AI come together to build real-life MVPs and business applications. Thank you, Sameh, for opening the day with a glimpse into the future hybrid generative AI. Stick around. We will continue after a short break. You can start now.
Okay, thank you, Yusuf. Hello, everyone. My name is Sameh Zaghloul. Actually, I'm working in the IT industry for the last 25 plus years, actually, in different areas. I started machine learning and big data, actually, let's say 15 years ago, and quantum computer 7, 8 years ago. Okay, so what we are talking about now, actually, is how to apply the new things, actually, from quantum computing on the things that we already know, AI and machine learning. Okay, I'll start sharing my screen now.
No, Mr. Sameh, the screen. Yeah, now we can see.
Okay, great, actually. Okay, as Yusuf mentioned, actually, this is the first, I guess, session, one of the first sessions in the DC MENA 2025. We'll be talking about the overlap and the intersection between quantum computing and generative AI and machine learning, okay, or what we call quantum GenAI. I'll explain how it.com at the end of the session, okay? My current role is Chief Technology Innovation Officer at Fix Solution Group. And actually, we are talking about the history of and overlap and the intersection between quantum computing and AI and machine learning. Okay, one questions actually. Let me start by creating some quick poll here at the site. I guess where is the poll? Actually, create poll. Which one started faster? This is a poll one. Which is older? Quantum computing or machine learning slash AI? Okay, option one, quantum computing. Option two, AI slash machine learning. Okay, and I guess I can create the poll actually. Let's start with something. This single choice. Okay. I leave this poll actually to the audience to answer. Okay, and return now to the history. Okay. In generally, I would assume that everyone will assume that AI started earlier than quantum computing. Okay, but this is actually not the case because as you see the timeline, quantum mechanics actually started like 125 years. So quantum mechanics theory actually started at the beginning of the last century, 1900s. Okay, with quantum mechanics actually was born. While on the other hand, actually machine learning and AI actually was born at mid 90s, 1950s. The first actually AI pioneers in this area created the first concepts and models and algorithms and theories actually in AI and machine learning. Okay, we didn't call it machine learning at that time. Okay, I believe all the audience actually will know this path actually from the evolution of AI since mid 50s to the AI winter actually at 70s. Everything was frozen. Of course, you know actually why? Because there's a lack of hardware resources actually to implement this AI algorithms. Okay, but this is starting actually to change rapidly. Okay, at the beginning actually of 90s, if you remember actually the big data evolution, mid 90s. Okay, this was the real start actually because we started to have efficient or adequate actually hardware processing engines to process this big data as we called it at the mid 90s. and start actually working on the big data, and then training machine learning models and AI models. Okay. The main inflection point here, 25 years ago, 2000, were actually supported with vector machine SVM. This is very popular, of course. I assume all the audience actually for the data science MENA actually event are coming from data science and AI background. So we all know that SVM, or support vector machine, actually machine learning algorithm, was one of the early algorithms that was developed in machine learning, and started from there. And I'll explain later, actually, at the end of the session, why SVM is very important. By that time, actually, during the previous 100 year, quantum mechanics and quantum computing was proposals only, and the quantum algorithm started almost at mid 90s. From this inflection point 25 years ago, the conversion or intersection between quantum computing and AI and machine learning actually start to happen, because uh, from here, actually 25 years ago, processing capacities, CPUs and GPUs started to grow exponentially. This allows us, of course, to process a huge volume of data. Not only this, to train machine learning and AI models on this huge volume of data. And this is already to speak now, 2025, with generative AI. Of course, this is very popular term, and everyone is working on it. This is high. But the main point here actually is what comes after AI, or after Gen AI. As you see now, quantum mechanics actually was born like 50 years before AI. Okay. And during the last, I would say, 10 years, we have seen actually eventual evolution in quantum computing hardware capability. Not yet, okay, because the maximum quantum computer currently is 1,000 plus qubits. We'll explain this later. This historical background is very, very important. And actually, I put here, actually, you will see this is a paper reference that I got from this historical evolution of and the intersection between quantum machine learning and history. All right. We all know AI and machine learning and generative AI, of course. Okay. What's coming next? What's after AI? It is not, it will not come. Actually, it is already happening. Okay. And it is growing. And the reason of this session actually is to prepare to what will be the dominant AI or machine learning within the next 3 to 5 years, which we call hybrid Gen AI and machine learning, hybrid quantum and the classical solutions. Okay, and this will bring us to the new topic here, actually. Okay, what is quantum computing? Okay, Yusuf, do we have a question so far? I'll assume that we don't have questions so far. So, in order to start correlating between the AI and the machine learning that we know and the quantum equivalent, okay, we need actually to understand something like this quantum circuit drawn in the lower left, where we have the input. But the input here, actually, you will see this bracket notation. This is a vector notation, as you call it, bracket. If we put it horizontal, actually, this will be ket 000, means horizontal vector. If we reverse it, actually, the notation will be column. So this is a matrix notation used frequently in quantum mathematics. It simplifies things, actually, that as we know. And the output will be also quantum measurements, or qubits. Okay, and quantum gates. I believe all of us actually recall the logical classical gates that we already have in classical computers, and we'll start using classical computing and classical machine learning to refer to the things that we already know, versus qubits and quantum machine learning and quantum AI that we're already discussing here, actually. Uh, how many number of gates we have in logical gates that we already all of us actually are using you will find a couple of handful gates, and, or, nor, XOR, and etc. Okay, so using this basic logical classical gates, we build all the algorithms that we're already using, including the one we're using in this our live broadcast. Okay, what about quantum gates? Quantum gates is a little bit different story, and here I started with this comics, SMB comics. They have something called the Quantum Talk, where they explain the basic principles of quantum computing and quantum mechanics in relatively simple terminology. The main screenshot that I'm sharing here actually is that how quantum computer actually do its calculation. So I'm putting these references at the beginning, at the end of the slides, and I shared all the references in the discussion threads for your reference. Okay, let's move to the next part. We all know the bit, which is if we go some analogy with a coin. Okay, the bit will be simply either head and tail or one and zeros. The one and zeros actually this is what we are already using and used to in all our algorithms and classical computing. Okay, what about qubits? Qubits is the same coin. Okay, the same coins means two things actually. It needs all exactly or almost exactly the space and storage space that a bit will have. So if you have a byte, which is 8 bits, so if you have 1 giga RAM and 10 giga RAM and 100 giga RAMs, actually you will multiply this by the number of bits. Imagine that you're already using the same storage for the memory storage and processing. Okay, you will have exactly the same coin, but the main difference here is the coin is flipping all the time, and they call it superposition. Okay, why this is important? Because the superposition is one of the three main elements in quantum mechanics that make qubit or quantum computing valuable. The first part is the superposition. This is the most important part. The bit or the coin actually can exist either in a zero position, zero value, or one at the same time, and anything in between. So this is what we call superposition. Okay, imagine that you are flipping the coin, okay, and you are measuring the coin, okay. If you see my hand, it will be head and tail or 0 and 1. This is the classical bit, okay. We have something similar actually in qubit, but instead, while flipping in the air, actually, it can have all the possibilities between 0 and 1, all the possibilities. This means that it can store many large volume of information. Okay, when the coin is flipped and I measure, we here actually the uncertainty principle for quantum mechanics, which we calling the probability nature of qubits. If you are why the coin is flipping, you are if you see this vector or arrow direction, this is vector notation, means that it is closer to zero than one. In probability, actually, this will be the percentage of measuring the coin as zero is 85% and one as 50%. Okay, this is the main probability. How to use this? Okay, and this is really actually the top important slide in this presentation. This is a very simple analogy between classical bit. If you see my cursor here, actually, either it is all the time it is 0 or 1, like the coin. Okay, the qubit actually is the same coin, but rotating on this sphere. They call it block sphere. Okay, and it is a unit vector, can take anything between 0 and 1. Okay, till I measure it based on the probability. The most important part here is capacity. Imagine that we have 3 bits. Okay, each one can be 0 or 1. Okay, so the different combination between three bit is 111, 100, 101. Actually, if you measure this using exponential 2 to the power 3, 2 by 2 by 2, eight different states for the 3 bits actually. And this system actually can take only one possibility of out of the 8 possibilities. So at any point in time, this 3-bit system is very small, of course, but it represents the example actually, use small numbers actually for clarification or demonstration. Uh, can be either only one state from this 8 possibilities, actually either 111 or 000 or 110. Actually, you will list this. Actually, you will find 8 possibilities. The 3-bit system actually can only contain, only hold or store or process only one state out of the 8. On the other hand, if you have 3 qubits, it will be stored almost quote unquote in the same storage capacity and same memory. But instead, actually, of having only one state out of 8, it can represent all the 8 states at once. All, actually. This can mean this qubit, the flipping, actually from the previous slide, this flipping coin, okay, and another flipping coin and a third flipping coin. This is a 3-qubit system, okay, can hold the 8 combinations of this state set at the same time. This means two things actually for AI and machine learning, that we can encode or store much larger information in the same memory or storage amount. And of course, most of you, I assume, that is working with generative AI and LLM fine tuning, and you have this actually challenge always the resources availability. You need some huge processing computers, a classical computer, of course, CPU with GPU accelerator with large memory. So if you have a very large language model, actually you need an 800 or 800 GPU with that huge 8 gigabit or and of course uh, the new models actually. So in the same amount, actually, imagine that you can store exponentially faster. So the example here actually, and this is very important, this is 3-bit Q system and 3-qubit T system. It can store 8 times the information that can be stored in a classical bit. Okay. What about actually if we take something larger? Okay. Let's say that we have 50 qubit or 50 bit, 50 bit. Okay. If we 2 to the power of 50. Okay. This will be 1 and 15 zeros. Okay, so this is a huge number actually for the efficiency of quantum computing that already quantum information that you can store. Okay, I'll just take a look at the online session to make sure that everything is okay. Okay. Samir, just to confirm, actually, my voice and video and the presentation is clear, right? Okay, great. Okay. All right. Okay, just making sure. So again, actually, why quantum computing actually will make a difference in AI and machine learning. Actually, it will make difference in everything, including AI and machine learning. The main point here actually is that if you imagine this bit, I can be either 0 or 1 at any point in time. The similar qubit at the same storage amount, memory storage, can have any combination between 0 and 1. If you combine this 3 qubits, the example here, any classical the 3-bit system will have only one combination out of 8 possibilities. The equivalent 3-qubit system will have all the 8 combination as the same system. So it is exponentially. So this is was 2 to the power of 3. Imagine that you have 50, that you have 100, then you have a million. Okay, so we are talking about some dramatic, not even exponential. Actually, it is much than that. And this is the fact actually that we need to start working on quantum machine learning. Okay, but okay, before actually going into details, actually we'll start talking quantum circuits, because what we see here actually is a quantum circuit. Okay, we'll start breaking down the component. So I'll skip for now actually for the last slide, which is this. Okay, how to start in quantum GenAI or quantum machine learning. this is the last slide in the play session, and already I shared these 5 links actually on the chat session chat. Okay, uh, I ordered this actually by the order of my preference, but of course it will be different for each one of you. It depends on the target. Okay, one of them actually is to have something like the quantum talk that we already discussed. Okay, here actually it is very nice, very nice, and but very accurate actually explanation for what you mean by quantum computing and what is the difference and what is the redefinition of quantum superposition, quantum entanglement, and quantum interference. And the screenshot I put, okay, is this one actually. This is the third phenomena of quantum mechanics, which is they call it interference actually. Okay. The second link, this is actually my preference actually for anyone to start. Okay. The second link, this is a comprehensive survey of quantum machine learning. This is a research paper that was just published 2 months ago. Okay. It contains mainly actually most of the overview of what was happening actually during the last 100 years in quantum machine learning and the evolution and available algorithms with practical use cases. So this will give, it is something like 100 technical paper, not that much, but it will give anyone actually need actually to have an overview, to grasp actually all the history very immediately. Okay. The third part actually, okay, I leave this. This is CERN Open Lab online quantum computing introduction course, published I guess 5 years ago. Okay, but I'll skip this to the end actually. And okay, if anyone actually wanting to start writing quantum machine learning algorithms today, immediately after this session, can actually use this link. Not sure why it is not clickable, but I'll just do like this and do like this. This is one of actually of the very easy to start up with quantum machine learning algorithms. Okay, this is of Benny Lane, one of the leading quantum computer and quantum algorithms. Actually, this is what we are interested today in quantum machine learning. And for example, the popular MNIST computer vision classification, you will find actually the quantum equivalent actually for it actually in here. You can download the Jupyter notebook. You can access it and run it locally on a quantum simulator. But this will discuss soon. Okay, and the last one actually is IBM Quantum Learning, which is Qiskit. Qiskit theoretically actually started something like 12 years ago. It was the first quantum algorithms or quantum machine learning and quantum computing SDK historically. So it is gaining very popular. It is so popular. But from my perspective, actually, anyone who need to start in quantum machine learning should start with Benny because it is very straight, very easy actually to adopt. But the trick here actually is in order to understand what is well written. For example, here actually, this is Ludep's MNIST explanation, and you will start reading this code. Okay, quantum circuit, quantum QML device, circuit layout, circuit depths, states, whatever. Okay, in order to understand this, you need the dictionary. Okay, the dictionary here actually it is this. This is recommended. This is quantum computing online course. I guess this was published 5 years ago, 2020. Okay, it has 7 modules, each one about something like 2 hours. So you are talking about like 15 plus hours. Okay. It starts with everything, the introduction and different protocols with different phenomena, the explanation, the applied use cases, a single qubit system and multi-qubit systems, and quantum algorithm for optimization and variational algorithm in machine learning, and a future actually. Okay. The second list is very important because this is the slides. The videos actually is something like 50 hours plus. but it was a size slide deck, actually 250 plus slides. It explained everything actually from scratch. Uh, and this is really very important actually for everyone to understand the new terminology, because I'll switch back actually after we load this to our original presentation, okay, to continue using some terminology. So this is one of the backgrounds that it is very important. And here till this PDF is loading, this is very important because if you are a data scientist or machine learning engineer or AI engineer working in a classification, regression, computer vision, object detection, large language model fine tuning, and generative AI and AI agentic AI agents and agentic AI and all of this, you will find a complete, stable and well documented literature and example and tutorials that you already learned some actually undergraduate, and you're learning part of it actually during your work and professional training and professional experience. But this is not the same actually in quantum computing, because the quantum computing age that we are currently living in is similar to the 50s or the 60s, when the first classical computer, mainframe classical computer, before invention of IC or integrated circuits, transistors. If you already remember the cathode ray tubes, the old TVs that you can see in the black and white movies, was not working with transistors. Actually, it is working with this is SPM actually that we are talking about, by the way. Okay, so this is one of the important link. You need to understand this. If you remember, actually, or the old TVs actually that exist in 60s, 70s, 80s, something like that, was working using cathode ray tubes, and it was not flat screen. It was like that, because at the back actually you will find the cathode ray tubes. Hard quantum computing hardware at the similar stage currently. It is still evolving. We're expecting this, everyone is expecting within the next couple of years, actually, we'll have a standard universal quantum computing, similar to the classical quantum computers standards that we already have in classical architecture, computing architecture. Okay. And also regarding quantum algorithm actually is, if any one of you actually has written some assembler code before, you will know the analogy actually, because writing quantum algorithm now is as difficult as writing an application using assembler. No one using assembler now, of course, unless he's already developing something very sophisticated and very specialized. But we all know using the high-level languages starting from C, C++, Sharp, and Rust, Python, Java, JavaScript, all the popular language, and Rust. Okay, so quantum computing, this is a spoiler alert actually. Quantum computer algorithm, or writing quantum algorithms, quantum computing code, or quantum machine learning code actually, is similar or analog actually to the assembler mindset. Because if you remember again, what is quantum gates? If you remember what the logical gates that you already have, and or nor XOR, couple of gates assembly, we are doing everything on the bits on it. So the AND gate will take, if the both bits are 1 and 1, actually the output will be 1. The OR, if 1 or 0, actually the output will be 0. If the two are zeros, actually the output will be 0, and so on. Okay, we are using this 5 or 6 actually logic gates in all algorithms that we are using during the last I would say 100 years now in classical computers. Okay, quantum gates actually is a little bit different, because it not acts on zeros or one. Actually, remember that the qubit is a unit vector on a sphere, so we can represent it mathematically with this. This is kid 0 plus kid 1 over square root of 2, for example, actually, and any can alpha and beta, any alpha and beta coefficients. So at the end of the day, actually, that would be transferred to matrix operation. So this is the X gate. X gate assemble at the input qubit will be multiplied with this unitary matrix, okay, and will be transformed. So this is matrix operation, matrix transformation. This will need some in-depth knowledge actually in numerical analysis and matrix operation explicitly. Okay, this is Hadamard gates, one of the very popular gates. Okay, it actually apply a conversion factor 1/√2 and multiply as the input vector actually by this matrix, and so on. This is controlled x. This is z actually rotation about z axis, and this is a two gate and triple qubits gates. So the number of gates in general are huge, unlimited. However, there are some predefined basic gates. The basic gates actually are used to construct almost all the advanced combination of advanced or complex quantum circuit and quantum gates. It will be single qubit gate, dual qubit gates like the CX gate, okay, and Z gate, or a qubit or more. Okay, this is the basic principles of the things that we know. This is an example of a quantum circuit. Okay, if you see here to the left, we have 4 qubits. This is qubit 0, qubit 1, qubit 2, qubit 3. The total is 4. Okay, and you will see that there are some gates actually applied. This is H, for example. This is Hadamard gates that we see in the previous example. Okay, and we will see also wiring between the gates. This wiring means that this is connecting the first 2 qubits. Okay, and treats them as single unit. Okay, and then after this, actually after the measurements, the T here actually is another gate, and at the end actually you will measure this qubits. Okay, so what is happening in between is we just converting all the possible or probability distribution, quantum probability distribution for each of these 4 qubits in this example, and calculating the probability and already calculating the factors and doing this what we call interference. So in this case, actually, we can highlight again very briefly the 3 phenomena actually of main phenomena or main features or main characteristics of quantum mechanics. One, superposition. The qubit can be either 0 or 1 and everything in between at the same time. Entanglement. This is entanglement that already this two qubits actually at the top, if you see my cursor here, actually are entangled. Means this wire connecting these 2 qubits. So whatever actually updates is the quantum state on the first one will affect the other. So entangled means connected. So we can connect 2 qubits, 3 qubits, multiple qubits, but of course there will be some hardware limitation currently. Okay, and the third phenomenon actually is we talked about superposition, entanglement, connecting multiple qubits together. Okay, and the superposition means that if you know this probability slide here, actually 85% 0 and 15% 1, you can actually expand this here. Okay, if you are measuring, and by mean measuring, actually imagine the flipping coin. Measuring means that you already measures actually and know if it is 0 or 1. Okay, if you measure this 4 qubit system, if you do a superposition, so interference actually, and adding all the quantum waves actually functions for the probability of the 4 qubits, actually you will end to the results. And this is, by the way, this is the most complex part actually in quantum mechanics, and this is, by the way, explained very easily here in this comic. By the way, as simple as if you have many qubits actually rotating together, each one has superposition and entangled together actually. The whole idea is just to chronograph a timeline actually. The pattern of interference where the pathing leads to each wrong answer interferes zeros each others, okay, destructively, and cancel out, while the path leading to the right answer reinforce each other actually, and you reach the answer. This is quantum interference explained very beautifully and accurately and very simple. That's why this link is very very important. So this was just example. Imagine that you are doing something similar using a quantum, sorry, a logical gates, one and zero and or. Okay, By example, actually, one of the early examples, the first, and I started learning quantum computing actually, I guess 7, 8 years ago. The first example, actually, the first exercise that I had as the first day is that write an assembler program that will take two numbers and add them using classical algorithm, using assemblers, ones and zeros. Okay. Then take this actually and write equivalent quantum algorithms that will add two numbers actually. Of course, this was some assumption. The number was 8 bits and 8 qubits in the second time, but this will explain the analogy. Okay. And believe me, actually, there is a lot of some naming convention that to be able to understand the new terminologies and the new thinking. And one important point here to be said, does quantum computing will replace classical computing now or the near future or the far future? The answer is no. Both will exist, will continue to exist like we'll see now. Actually, it's a hybrid world is hybrid. So we'll have all the time classical computer as we have now. Part of the processing is done using classical computing. Okay, only part of the processing will be done on quantum computing for the difficult parts that we cannot do now or can do difficulty on classical computer. So they will both exist. So the hybrid system is the future. So these were we are talking about what we call hybrid quantum machine learning, or hybrid QML. Okay, again, quantum computing is working totally differently than classical computers, and it will not replace classical computers because actually we still need forever, okay, classical computing, because any input or output for the data actually that you are working on much goes through a classical computer. Imagine that you're already writing any application, not necessarily AI or machine learning. The input actually taken from the all devices, keyboard, the mouse, internal IoT systems, API calling, logs, whatever. All this input actually will be handled the same way as we do now. So all the input coming from the data, actually, of course, the data actually will go to classical computers and run classical algorithms for data preparation, data pre-processing, etc. And then after preparation, it will be fed into quantum circuit or quantum computing backend. Okay, do some magic calculation on only small part of the workflow. Okay, and then apply the quantum algorithm. This is the one we are talking about actually. This is still a very huge area for R&D and development. After it already complete, actually it will measure all the qubits and return the output as data, bits data, where we can see and interpret using our classical algorithms and classical computers. So the world is hybrid, and quantum machine learning and quantum GenAI is also hybrid. This means that you cannot do everything in a quantum computing, AI and machine learning, or any other. By the way, you will need actually this hybrid classical quantum combination. Okay, this is very important point. Okay, let's go try to go some deeply. Okay, and we'll take some examples that I believe all of you or most of you know. Image classification, MNIST data sets that we already talking about. We are here actually, this is zero. Okay, MNIST data set, of course, zeros and one classification. Okay, here actually is this will be similar to the input layer. Okay, of course, this is very small, actually 4 qubits only. But and this is very nice actually. Let's take an example. What you do generally when you do some computer vision and deep learning using CNN, for example, convolutional neural network. Okay, you will take each image. Okay, for simplicity of calculation, let's assume this 10 by 10 image, 10 pixels by 10 pixels. So it contains 100 pixels. So your input layer for the neural network, classical neural network, okay, will be 100 bit or 100 node. Okay, remember when we were talking that okay, a single qubit can take much more information that a bit can take. So simply speaking, here actually we can, instead of, for example, this naive example, 100 node input layer for our neural network, we can actually abstract it to to couple of qubits. And this is the beauty and the powerful and the power of quantum machine learning, that we can actually work on the same large, huge actually data, and much more larger that we cannot process now, and abstract or encode. Okay, I'll return in a minute actually to what we need by encode. Encode classical information or data to quantum information, and this will be, we are doing here a huge dimensionally and volume reduction, because we can represent a large number of bits or classical bits actually in a much fewer number of qubits. So this is the first part. So this is the input layer. After I translate my image data actually to from classical data, RGB colors or stream from 0 to 250 50 that you already all know. I encode this encoded data. We'll explain in a minute actually what we mean encode. Encode means you take the data coming from multiple bits or multiple data points or multiple features, and encode its value in a much smaller number of qubits. So this is the first important part. I have a huge input data that I need to process and train my machine learning and AI learning on it. Okay, I can reduce it dramatically, and I mean dramatically actually. Imagine the example between only one of 8 possible states for 3-bit system to all the 8-bit possible combination in a 3-qubit system, and just replace this 3 by 100-bit and 100 qubit, 1000 qubit by 100, 1000 bit by 1000 qubit. Okay, you will find actually the difference is really huge, and this is the real potential that we need. All of us actually need to work. What is coming after Gen AI or AI? Okay, and this is very important. Uh, this is the encoded part. Okay, then we have here actually quantum circuits like the one we have just seen here. Okay, it will do something. It would apply Z gate, for example, on the first qubit, and X gate on the second, and Y gate, and the third Y. It's a rotation about Y axis, Z rotation about Y. Okay, and do some entanglement, connecting the first 2 qubits together, and 3 and 4 together, and 2 and 3, and apply another number of gates. Then finally measure. The measurement here is as simple as, okay, and this is really important. Again, imagine the flipping coin. Okay, all the area here actually, these 4 qubits are spinning. Imagine that you have 4 coins, and somehow actually you managed actually to spin the 4 coins simultaneously, and doing your calculation. When this coin collapse and you measure, okay, 1001, for example, this is we call the measure. The measurement here mean two things. Based on the probability distribution or quantum wave function, we will measure the final measurements of the 4 qubits based on the probability distribution, and also you will collapse the quantum state. And then actually you take this data, doing some prediction and doing some comparison and evaluation for the loss. Okay, and this is a back propagation function, of course. Okay, where actually you are, for each iteration actually you elevate your loss function, and you always try to minimize the loss function based on the activation functions that you are using. Okay, then apply parameters and reiterate. So the first part actually is encoding. Okay, the middle part actually calculations is quantum neural network, and the prediction, evaluation, and optimization is using the same classical machine learning algorithm. This is one example of the hybrid. So we are mixing both actually. We are making use of the something that we know work well, okay, with the new thing that works much better actually in larger marshal data with the quantum neural network. Okay. Now, actually, we mentioned here actually 3 things actually. Okay, embedding. This is the most critical part in quantum machine learning. Then quantum circuit, a little bit difficult, but it is, of course, important. The architecture of your neural network, how many layers, how many gates, what is, how many layers, how many qubits, and what are the gates, quote unquote gates, or mathematical formulas you will apply actually to answer, then the measurement. We'll start with the data encoding. Encoding, this is the helper space. This is the sphere where the qubit is living. It is a unit vector rotating in this helper sphere, okay, and can take anything between 0 and 1. So from you have your classical data, okay. You have your data, you have data set actually that you need to do that machine learning training on it, okay. And the first things you need are you take each feature actually and encode it to qubits or multiple qubits. Then start working on it on a quantum circuit, okay. Then measure the results, evaluate, minimize the loss function, reiterate till you find. So this is the first critical part, QML or quantum machine learning data encoding. Data encoding can be as simple as I'll just remind you with this drawing here. Keep this in mind: a sphere, okay, with a unit vector, okay, traveling all over the sphere, not coin, okay, and can take anything, okay. There are many types of encoding. Amplitude encoding is that, okay, I put some amplitude actually for this qubit corresponding to the value. So if this feature, this point actually is point 0 actually, so I'll initiate the quantum, my qubit actually, with something equivalent to this point 5. So it will be 50% charged, okay. But remember, actually, it is a vector, so it has angle. So I can combine this with angle encoding. So the angle with respect to x and y and z. I can use actually this to encode additional information. Okay, and I also can use what we call phase encoding by analogy with sine and cosine waves. Okay, that you most probably seen before. Actually, I can assign the data or classical data input to a specific phase for this rotating qubit, or just basic encoding without any intermediate calculations, or dense encoding. Dense encoding is very advanced. Instead in one-to-one analogy between a bit and the qubit, actually, it is multiple bits actually to multiple qubits entangled together and controlled together. Okay, this is the 2-bit gates, 3-bit gates, and multiple. Okay, I assume that at least one of you actually will ask when to use which encoding. Am I right? Okay, so it depends. The answer, it depends. Okay, and the challenge here actually is this new algorithm is not that new. We are talking about first matured algorithm is here actually since something like 10 years. But mature quantum machine learning algorithm. Of course, quantum SVM actually is 25 years old, and they'll refer back this later. So selecting the right encoding, it depends on the nature of data, volume of data, okay, and the architecture of your quantum circuit. So there are many parameters, okay. This is where actually we need actually, if you see the references in chat history and the last slide in this presentation, already I included some references. One of them actually this online quantum computing introduction course organized by CERT Open Lab a couple of years ago, because you need actually to know or to learn actually these new concepts. And again, I do some analogy for myself actually. This quantum algorithm actually, the difficulty level actually is similar, if not more, like doing writing a program using a simpler language. So you need to understand the new concept, because it is not just new tools or SDKs or frameworks. This is a new concept or handling the quantum information. So in data science, actually, we handle quantum information, and this is very stable, very tested, and you will have very a huge amount of literature, courses, training, and experience for real life projects. Okay, the equivalent quantum algorithm actually is not that actually, because we don't have quantum computing projects or quantum machine learning actually running into production, there are very, very few, and they are very new, actually, new and few. Okay, so the accumulated knowledge actually is expanding. This is exponentially increasing year over year with much higher rates than before. Okay, so we need actually to understand this new areas and the new terminology. So the first important part for you as AI engineer or machine learning engineer or data scientist, know the basic principles of quantum machine learning encoding, different encoding, when to use which. Okay, based on the data, quality of data, size of data, shape of data. Okay, and of course, second part, what is the architecture of your quantum neural network? How many qubits? How many layers? Okay, what type of gates actually you are applying? Okay, you will find actually that these are a couple of combination. And of course, a side comment. Of course, we all now in the Gen AI and agentic AI agents, where if I'm data scientist or a developer or software engineer, actually, I can use available Gen AI tools actually to accelerate my work, developing scripts, debugging code, writing some documentation, doing some integration. Of course, this accelerate our daily work, day-to-day work, including myself. Okay, what about quantum algorithms? Do we have the same advisor agents actually that will assist me during building a quantum circuit, for example, or choosing the right algorithm for encoding my data? Not yet. This is something ongoing as we speak. So if you ask any Gen AI, actually, I need to build this quantum circuit. Actually, it will answer from the limited, discrete, and not unified information that already we have now worldwide. Okay, and this is again, I'm making some analogy here actually with 60s, for example, when we have the first mainframe, it was very huge, stadium size, and did not use integrated circuits. Okay, it used a cathode ray tubes. Okay, and we are people were doing actually programming using assembler. Okay, so we by analogy with quantum computing, currently we are in the middle of this actually. So the universal quantum computing, universal standard for the computing hardware part and the quantum algorithms, okay, is still evolving, but it is time actually to work now. Okay, as I mentioned, I started working in this actually like 7 8 years before. Okay, and I know people actually as of 25 years actually working in this in Egypt, by the way, not only worldwide. Okay, because this is what is coming already. So if everyone is now talking about AI and generative AI and agentic AI and large language models, okay, this is what happening and evolving and will continue evolve, by the way. Okay, but there is something had already came up 125 years ago and start we realized, if you remember the history as the first slide, during the last 10 15 years we started to see something happening with availability of quantum computing resources, okay, for this. So actually if you are talking about building your career or enhancing your career within the next 5 years actually, so of course AI is a must, is a must, of course, but quantum AI actually is also a must because after 4 5 years actually everything will be hybrid. Okay, so back to encoding. This is an example for amplitude encoding. So the value for the qubit is simply like the feature. The feature is 4.5. This is also 0.5. And the second approach, binary encoding or basic encoding, like the previous slide, as simple as I just take everything as it is actually and put it in matrix notation or bracket notation. This vertical bar and this bracket actually they call bracket notation, which is as simple as very simple matrix notation between distinguish between vectors and rows. Okay, or angle. Okay, I take the data of the feature and convert it out to the angle for this qubit actually and store it there actually and start the processing. Of course, the encoding approach is dependent on data type, shape, quality. Okay, and the quantum circuit by quantum circuit or quantum neural network gates. So you need actually to start to pick the right encoding with the right data and the right. So this is work in progress. Okay, let's take it to the next level. Let's take this to the next level using quantum neural network, but adding what we call variational circuit architecture. Variational. I believe many of you has already worked in classical, and I use classical quote unquote now, autoencoders and variational autoencoders. We use this in classical algorithm actually to encode huge volume of information into much dense or smaller, okay, then doing our processing, then actually reverse it back, okay. So this will enables us currently of doing calculations on huge volume of data that in the relational algorithm other than autoencoders it is not possible, okay. So this already we have already, and we are working with it during at least 10 years actually. Autoencoder or variational autoencoders in classical variational autoencoders, okay. Now we have the quantum equivalent, quantum variational autoencoders, okay. If you remember, the autoencoders actually the main value is simply one of the use cases is data dimensionality reduction. So instead of handling 100 features, I'll I'll treat only 5 new features actually that will have the same probabilities that were included in the 100 features. This was, of course, very important. Okay, what about introducing quantum computing in the area, encoding this 100 features, okay, in less than in 5 features, but taking this actually further, okay, and encode it in qubits. So instead of a maximum handling 100 feature, 200 features, 300 features, and doing some dimensionality reduction or feature selection or BCA, principal model analysis that already used for dimensionality reduction and continuing on it, I can take data sets actually of 1 million column or 1 million feature. Uh, does any one of you actually has worked with one data set with million feature? I did it personally, so I doubt actually. This is not possible actually with the hardware what we have now, the classical computers that we have now. But with quantum computing, this is possible because I can simply actually the 1 million feature. Imagine that you have data set with 1 million column or 1 million feature. Actually, you can actually do some feature selection, of course, and conversion this let's say using something like BCA or something like that, based on code analysis, dimension learning, but you will still end up with huge number of that actually you cannot process in the larger computer or supercomputers that we have now. Okay, so what about encoding? And this again, the encoding part is very important. Encoding this huge number of data to much smaller qubits that will fit in the same memory, because this is very important. The bit and qubit will almost quote unquote will take the same memory footprint, okay. And in this same memory actually you can store much more data actually in it and start the processing. So this is a high level architecture. I have the same data sets features, okay. I can do on part of it, for example, block encoding, and I can do on part of them actually amplitude encoding, and I can do actually what for example rotation encoding, x y or z, or combination. I can do dense encoding, whatever. But anyways, actually, I apply the first layer of data encoding. This, the variational block, this is horizontal line actually is my layer, okay? And this is the size of the network, okay? And I can, like neural network exactly actually, I can have multiple layers uh, across multiple qubits with variant number or types of gates. It depends on what, the algorithm. So the quantum algorithm, again, this is require very good math understanding and matrix notation understanding. I can do equivalent here actually, and then I measure. This is the measurement. With, remember, as soon as I measure, I collapse the feature and measure as a result, and run this on the cost function and optimizer, and do the iteration till I reach to the minimum cost actually, and we have a stable. Of course, you all of actually like to see this actually. My network actually is training and optimizing, minimizing its cost function till it is stated actually. So this is the final answer. So the equivalent is there using quantum variational circuit architecture, and the benefits is very huge. What algorithms? This is a very, very nice question. What classical algorithms currently covered by or cover or has its equivalent quantum algorithms? Almost all of them actually. Almost all of the classical machine learning and AI algorithms that we classically use every day now has already equivalent quantum algorithm or hybrid quantum algorithm, of course, to be exact, that we can use actually hybrid classical and quantum computer backends for processing. Okay, the oldest one again, quantum SVM. I'll refer to this better. Of course, the stability and the maturity for quantum algorithms actually is different because it depends actually when it was started. Actually, the ecosystem, how many developers and data scientists and machine learning engineers are working on it actually, and debugging, discover some bugs, correcting, adding new features. So this is accumulating with time. Okay, and this is finally actually just enlarged view of quantum variation autoencoders. The same classical approach for autoencoders or variational autoencoders, classical, that already all of us know. I have my input data, I have the encoder, will encode this huge data and much smaller. For classical autoencoder, actually, it can do a huge reduction. In quantum variational autoencoder, actually, it cannot do actually not huge something with huge actually to the power of 100 zeros actually as the top, 100 zeros top. So this is dramatical difference. And do my calculations and all the processing or the training, the measurements, whatever I do here actually, then after I result actually, I decode again this and try to reach actually the same inputs that I have. Okay, this is the same classical variation autoencoders that already using classical machine learning. Okay, the difference actually is I can do it now using quantum computing, quantum algorithm on much larger set of data. Okay, all right. Now, okay, do we have a real quantum computers actually accessible to do what we all have discussed so far? I believe this will be one of the main questions, okay? Because if you have quantum machine learning on quantum GenAI integration, this is quantum classical hybrid workflow. This is the engine in my code, okay? That will have some classical algorithms, of course, for data collection, data acquisition, data preparation, everything, okay? This will be part of your Python or notebook, actually, or Rust or whatever language that you're using, okay? It will access the data, okay? And you have machine learning libraries, actually, is a classical one. You will continue use the classical machine learning. So the same like actually quantum computing will not replace classical computers. It will exist in a hybrid system. Classical machine learning libraries and SDKs that we're already using will continue to use, but we'll have also new quantum algorithms. Actually, this is the one who's gaining building maturity over time, and we will use both. Depends on the best fit. Okay. Of course, classical algorithms will run on classical computers or supercomputers or workstation or whatever. Quantum computer will be this new part, actually, quantum computing backend. What we mean here by quantum computing backend, either real quantum computer, and these are very few as we speak. We'll talk about the limitation in a minute, or quantum simulators. So if you, for example, look at the chat history for this session, you will find multiple links. The third links was Penny link, quantum machine learning tutorials and the demos and libraries and the ready-made code explanation. Okay, you can download Jupyter Notebook and run it locally on your machine. Okay, so the question here actually, how I can run a quantum computing algorithm in a classical computer, my laptop. Okay, this is where actually the term quantum simulator come into place. Okay, any existing classic hardware can be used just abstraction open source library simulator. Okay, can simulate a real quantum computer with limitations, of course. Okay, one limitation actually is the size of qubits. For example, my laptop, in a normal laptop, for example, uh, can simulate something like 10 to 20 qubits, okay, and will be a little bit slow, of course, actually. But this means that you can start developing quantum algorithms and testing the algorithms now, immediately after this session. You can start developing or running quantum algorithms in your laptop, actually, in home or at work, okay, developing and testing and learning quantum algorithms and even optimize this. And this is what we really happen actually. Anyone actually working in quantum algorithm development, including quantum machine learning and AI, will 90% of the iterations actually will use it in his development environment. Okay, development environment not necessarily you not need necessarily access to quantum computer because they are a little bit rare as we speak or limited access. Okay, but you can do 90% actually of course the data acquisition, encoding, building, comparing different encoding techniques, different number of qubits, different quantum neural network architecture, different number of layers, different optimizer. So of course, we all know that any data science experience will run multiple iteration to reach on a sample data, of course. Okay, to reach actually some stable actually and start to test it and train it on larger qubit. This is the last 10%. The availability of quantum computing backend, real quantum computer actually is mostly cloud. In some countries actually they have some quantum computers with relatively high capacity or processing quantum processing power more than 1,000 qubit. But this is actually not available for public access. A little in small countries. There is new waves actually of smaller. By the way, 1,000 qubit actually is not done enough. Is not enough actually. This is an R&D platform. So the real number or the real size of capacity of a quantum computing that will start to make difference in early late life when we reach something close to 1 million qubit. Currently, the maximum is 1,000 plus, but it is expected within the next few years, actually, we'll have something close to 1 million. Okay, but this is coming. But as we speak, there is a couple of quantum computers, something like the maximum is 100 qubit, like from IBM or Google. Okay, there are smaller sizes. There are available quantum computing platform. Part of, can give you some free tier actually to test your algorithm. So what I usually as a researcher or developer, okay, I work 90% of the time actually on my simulator, laptop, server, supercomputer, whatever, okay, to develop and test and iterate and enhance my algorithm. Then I keep the last 10% of the runs actually on a quantum computer actually, okay. So this is normally what is happening, and this is by the way similar to any DevOps environment in software engineering, continuous integration, continuous development. Is the developers actually are using this laptop as development environments, very small, okay, development environment. Then you can merge this code actually to the staging or testing environment where we merge the multiple codes from multiple developers. Then I start using doing some test unit testing, integration testing. Then I already start going to the next phase actually using some UAT, user accept testing. This all can be done actually in a classical simulator, a quantum simulator on a classical computers. Okay, only the production part when I'll start instead of handling a small data set or relatively small data set, I'll start using a big computer. I'll start switching. Okay, and to be accurate, there is also one dimension Okay, why we need actually to run any algorithm finally at a real quantum computer? Because a computing simulator is a simulator, so it does not simulate many things. First one, the probabilistic features of the qubit. This is usually classically called uncertainty principle in quantum mechanics 100 years ago. Okay, so it is a simulator. So I don't have real quantum computer spinning electrons or photon. Okay, working randomly or moving randomly. No, I have some pseudo code actually or pseudo simulation algorithm to simulate this electron. Okay. Also, the hardware connectivity. If you remember, if you look at this, for example, this lines here, yeah. These lines here mean I'm wiring two qubits together. This is hardware wiring. Co- Currently, there are some hardware limitation actually on how to implement this wiring. So the simulator actually will wire anything because it is just a simulator. Okay, but actual quantum computer will do some circuit optimization or quantum circuit optimization first and then start the processing. So this means that my experiment I'm running currently, for example, one time on a classical machine learning experiment. I ran it only once with multiple iterations, of course, okay, on a classical computer, okay, and I'm sure that the results actually is almost the same if you adjust the seed factor actually at the beginning of each training machine learning training model, okay. But in quantum computing, it is different because remember actually this flipping coin. This means that in order to test the probability, quantum probability, and the non-certainty principle for quantum mechanics, actually, you need to run the same experiment actually after you make sure it is functionally correct. Okay, you need to run it actually 100 times, 1,000 times, 10,000 times, and take some average and mean actually to reach the conclusion. So this is another part. So again, almost all LMS have its equivalent. The quantum variation autoencoders, already we are using this in classical quote unquote variation autoencoders. We have the quantum variation autoencoder equivalent now, which has very good processing. And this is the quantum backend. This is the challenge, by the way. Okay. So talking about the integration for a hybrid integration, and classical machine learning SDKs and frameworks and the quantum machine learning SDKs and frameworks. There is a lot actually. The first one arrived actually, this was the first one, IBM Qiskit. This is open source quantum information software development kit actually. This is, I would say, everyone started in quantum computer actually started with this actually because this was the only thing actually 12 years ago. So I still remember this actually when I was working using online Jupyter notebook and writing Python code 10 years ago, 10 years ago, writing Python code in a Jupyter notebook actually and accessing quantum computer backend. So this was actually, this is what it is. Many other languages, and again, the standardization is ongoing. Okay, the recommendation is to start quantum machine learning, quantum.ai. The first thing actually, the first choice, Benelin.ai. Okay, they have their QML optimized actually framework. So this is the one you should start with. Okay, so is it really actually utopia, quantum machine learning? You can do everything. Not that, because we still have some limitations. One of them actually, large data sets actually cannot run currently on a quantum computer because we don't have the efficient or required computing capacity, quantum computing capacity to handle this data. But again, as I mentioned, within the next few years, actually, if we reach actually million qubit quantum computer, actually, we can do exponentially much faster and process much larger data set. Imagine that you have GenAI large language model like the new one with 400 billion parameters. Okay, okay, and in order to train this, you need a cluster of, for example, 64 GPUs, 64 nodes. Each one have four to eight NVIDIA GPUs with 160 gigabyte RAM video memory to fit the model in memory. Imagine actually that with all this huge number or size volume of data to train the neural network that you're using is your GenAI model actually, you will have the same capacity actually, but in quantum computing. This means that the 400 billion actually parameters that we are using currently can be encoded in much slower, a smaller number and fit in one GPU, for example, or one quantum computing node. So this is what we expect to happen. Actually, this will dramatically accelerate the evolution of AI and everything else. By the way, the second drawback here currently in quantum computing actually or quantum machine learning is that the error rate actually in current quantum computing. So it's difficult actually to keep 100 qubit and 1000 qubit spinning. Imagine that you have one coin is spinning it and controlling. So imagine that you have 10 coins, spin, 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 okay, and control them, okay. If you have 100, 1000, the error rate actually is still high, but this is actually is becoming better over time. So actually, we are very close, actually. Okay. Now, what this is actually a theory, and what is quantum GenAI? Quantum GenAI.com actually is an MVP, minimum viable product that already working. We developed, I guess, 2.5 years ago now in Hex solution. This is working, and this is high level features. This is a GenAI solution for handling large volume of structured and unstructured, semi-structured data in Arabic and English and multi languages, and they do some information extraction, embedding, and vector indexing, and doing some what we call graph reg, building the knowledge graph, and use it actually and retrieving knowledge from your data. Okay, this is a classical use case that very popular, everyone is working on it. But what we added actually a couple of years ago is that we added a pilot for a one module using quantum SVM, quantum support vector machine. We started actually with one of the modules for quantumGenAI.com. Our MVP product now. It is currently this is working, and we are early adapters, so we could get this domain at that time, quantumGenAI.com. So this was one of the branding or marketing decision actually when we started the MVP. We have a module, okay, used for domain classification. So if I have 1 million document of my data set, okay, I need to do some quick classification for domain. This is documents talks about sports, politics, life science, whatever. Okay, so the first actually our document domain classification actually we used SVM, the classical SVM, to do it a couple of years ago. Then we started actually to replace it with a quantum SVM, the same SVM algorithm but running on but using quantum equivalent quantum SVM, and running currently on a quantum simulator, by the way. So if you access quantum GenAI and request trial, for example, you will find that this QSVM is used currently on a quantum simulator backend. One server is 128 cores, for example, to do this simulation and can process millions of documents actually. Okay, why we did this? Because, and this is really the important part here actually, this is one of the main messages that we need to communicate here actually. We know all the constraint and unavailability of existing quantum computers. Okay, very difficult, very costly. If you need actually to build a reasonable quantum computer on site, on prem, okay, the average cost, one of the surveys or I just seen last month, the average cost of a decent quantum computer, not like 10 qubits or something. This is a toy. $100 million. So an average. So at average, actually, if you need to have your own in your organization a quantum computer, you need to pay $100 million. This is a business case not available currently. Or go to quantum computing cloud. Okay, and this is still very expensive as well. Okay, but this is coming. Okay, so again, why SVM? Because SVM was the first, one of the oldest oldest or legacy quantum machine learning algorithms that already ever exist. Support vector machine, very popular, not accurate in many use cases, but it is stable. Okay. And the first, imagine, okay, I guess all of you now can answer the question. What was the first quantum machine learning algorithm that the people are start seeing 10, 15 years ago? It was quantum SVM. Exactly. So this was a choice. We selected a stable quantum machine learning algorithm like SVM. We tested all the tries, and we are currently running on a quantum simulator backend, normal computer with a simulator layer, a little bit slower, by the way. Okay. But already after we did this in development, actually, we tested this on a quantum computing cloud. We paid a lot of money, actually, but we did some final testing now, and we have something ready. Okay. Why you are doing this? This was part on a hackathon in the region, AI Gen AI hackathon in the region, and one of the ideas that we introduced that we will have built a quantum Gen AI hybrid system. Okay, this system almost has 10 modules. Only one of them currently is using quantum algorithm, quantum SVM, and running on a simulator. Okay, but we are ready actually with a tested hybrid architecture. Okay, if next year, for example, a customer in any country actually has access to a quantum computer, and some of them starting having now in our region, at least Middle East and Africa region, okay, we can actually benefit from quantum GenAI, okay, because I'll just, instead of, I will not change the code actually, I just point to another backend. Remember this backend box? This backend, dynamically using this classical hybrid workflow, I can start to develop and test on a quantum simulator and just point to a production real quantum computer as a production level. This is normal actually. So that we have, this means that quantum machine learning is not a dream. It is not something to come. No, it is there. Okay. By the way, in this hackathon 2 years ago in the region quantum Gen AI hackathon, we won first place because actually we are building for the future. Okay, because next year, 2 years ago, 3 years ago, think about a couple of years ago, because this is a product development, took a lot of research, a lot of debugging. Okay, but you are ready actually now to work a hybrid a system, quantum GenAI, and this is very good. So this is a practical, real life, regional experience from here, Egypt and the Middle East, actually, that is using quantum algorithms in production ready platform. It is an MVP phase actually now during the last 1.5 years, minimum viable product actually, but we are expanding. So this is the future directions. But I guess we already talked mainly about to future many challenges and many opportunities. Okay, the main two challenges here, and I'll use again the analogy with classical computers in the 60s. Okay, large computers using cathode ray tubes actually instead of transistors that we have now. So, but if you remember Moore's law, you
So,
can
Sam,
have double
sorry for
transistors
interruption.
every 2 years.
Yeah,
Okay,
sorry for
this is
interruption.
already
We're
coming.
having two questions in the chat. The first question. Yes.
Okay,
The
yes,
first question is
okay,
asking about
very good.
website. Abdullah is asking, is it quantumgeni.com with N as in Nancy or M as in Mary?
Sorry, there is a lot of background noise.
Is it better now? Yeah. Okay.
Okay, Yusuf.
Okay. So
Yes, much
first
better.
question is asking about the quantumgeni.com website. Can you type that website on the chat? Yeah,
This
he's
is in
asking
the
about the website.
questions.
He's saying, is it Quantum Gen with N as in Nancy or M as in Mary?
I'm reading the question now. Islam Salahuddin, actually, how many years actually will it likely take to reach wide
Okay.
market availability?
Yeah,
This is a very question, right?
that was one of the questions.
Uh, okay. I guess I partially covered this actually. We are expecting actually something from 5 to 10 years, but can happen faster or slower. Okay, but of course there is one fact here actually. Let's see the 100-year evolution of IT technology. Okay, and the rate starting slowly, and then the rapidly exponential. So, for example, in today's session, we were talking about a comprehensive machine learning survey done 2 months ago, but it is now a little bit outdated because just last week actually there is a new image transformation hybrid algorithm using quantum computer. So it is okay. Let's say starting from 5 years, actually, you will start to see something. Will it explainably still be possible to achieve with quantum machine learning? Yes, of course, actually, because remember the encoding part. Okay, so you can process much larger data sets. So the answer is yes. The second question from Abdullah Abu Zakri. Is Quantum GenAI with M or M? Quantum GenAI with M actually. It is there in the chat, by the way. Or I write it here actually. Quantum GenAI. Sorry.
And there was one last question in the chat.
Can I edit?
Muhammad Rashad is asking,
Yes.
how might the integration of quantum computing with generative AI impact specific industries, such as financial modeling? And can you provide potential use cases for some real world applications and industry specific implications?
Yes, actually, all the use cases actually here in this link I shared in the chat. I'll share it again actually on the questions answer. This is the comprehensive survey actually that I was referring to actually. This is a really beautiful document, a technical paper actually, 100 something like 100 pages. It talks about all the history that we already talked about today, and all the algorithms and different current states and current use cases, including financial sector. By the way, they are using quantum algorithms for the market decision optimization and stock trading. By the way, which is, by the way, of course, decision optimization is one of the complex areas. So we have actually production like quantum GenAI, quantum machine learning use cases currently running as we speak. Very few, but there is a lot. This link actually here. I'll just post again the content of the last slide, actually, where it contains the links. I posted again now on the question answer thread. Okay, it has 5 links actually. This is the comics, actually, the quantum talk. This is a very nice starting. And the second one, the comprehensive quantum machine learning survey that already I've reviewed. You will find all the information that you need actually about anyone in the org. The third one, this is my personal recommendation. This is a little bit difficult. We'll need some time actually, but a certain quantum computing course, online course, and the material here. It is 5 years ago, but it will. You will see the first slide actually talking about what quantum computers existed 5 years ago, not now, of course. This okay, but the remaining part actually, this is the first 1 hour of the course. The remaining 15 or 16 hours actually is talking about quantum mechanics and quantum machine learning. And this is theoretical background that we need to understand the vocabulary and to start working on it. Okay, and of course, Benny Lane, the Benny Lane quantum machine learning platform. If any one of you actually interesting to try actually quantum machine learning now, immediately after this course. So please go. I'll repost it again in the question answer alone. Okay. Go to Benny Lane actually and start writing and testing quantum machine learning code now.
And Mr. Sam, I just need to remind you that we have just a couple of minutes before we end the session.
Sorry, Yusuf, can you
Can you
repeat
hear me
again?
clear now?
Yes, but there is a lot of
Okay, so
background noise.
I
But
was just
please
saying that
continue.
we just have a couple of minutes before we end the session, so you can wrap it up.
Okay, great, great. Actually, I'll just use. I'll just share my screen again for the last 2 minutes. Okay, and I'll focus again on the last slide because actually uh, the objective of the session this is 1.5 hours, which is almost finished now. Okay, there's not is not enough for sure actually for to go completely in quantum computing and quantum machine learning, of course. But the two messages here actually, quantum computing is there and it started 50 years earlier than AI. I saw in the poll actually it is 50-50 actually. But actually, yes, as we saw on the history timeline, that quantum computing started 50 years before actually AI. Okay, and uh, exactly like what happened actually during the last couple of years, since Google has came up with BERT architecture. Bidirectional represented transformation from encoder. This is the main architecture, okay? The main difference, the turning point in the generative AI and large language model, this happened just a couple of years ago, okay? And all GenAI actually, development actually is using this there. So this was an inflection point when Google, for example, developed the BERT architecture. This is everyone is using now as of date, like Llama 4 actually 3 days ago, of course, you heard about it. So the inflection point now actually in the quantum machine learning actually already happened 2-3 years ago. We start having some quantum computers actually tangible, okay, that we can test on it. So for example, there are very few free tier, but actually we have many actually 100 qubit plus. So the inflection point happened already. So it is at the time, but it is not that easy. So the first part, this is my advice, and this is exactly what I posted twice on the chat and the question poll. Please start with the quantum talk. Very nice, very easy language. Okay, to explain the very complex terminologies like superposition, entanglement, and interference in a very simple way. Okay, then if anyone interested actually to know all the history and the surveys, like one of the question, where is QML is implemented now? Okay, you will find all these details in this small technical paper. This less than 100 pages actually, not that small. But the most invaluable part here is in it actually it is has something like 300, 200 or 300 cited references. So it is a huge source of information in a single technical paper. And my preference, okay, is just spend 1 or 2 weeks actually in quantum computer to know the terminology in this actually online videos, some videos, and the PDF actually that we seen together. Okay, but again, this is very important to understand the new terminology. We're talking about embedding, amplitude embedding, rotation embedding, angle embedding, all this actually. Hadamard gate, T gate, CX gate. Okay, you need actually just to know the terminology first, and then actually you can start developing quantum machine learning today. Yani actually after we finish this section, if you don't start now, okay. And if you want further actually learning, you can continue with the cascade with something. Some people consider it the first SDK, quantum SDK is a market, so everyone knows, and that a great ecosystem. So okay, that's it. So if I need actually to close with something, sorry, just to go to Benny Lane, okay, and start experiment. I'll just post it here once again, okay. Quantum machine learning, okay, it is loading. You can select actually what you pick actually. MNS is very popular for you actually, so we can start download the notebook now. So please start learning.
Thank
Okay.
you. Thank you so much, Mr. Sameh, for opening the day with a lot of information. And thank you for starting the day with a glimpse into the future of hybrid generative AI. And that's going to be
Okay.
all for the first session. Now stick around because we will be having like around 15 minutes coffee break, and then we're just going to start the next session within 15 minutes from now.
Okay.
Thank you, Mr.
Thank
Sameh.
you, Yusuf and team. And please start developing quantum machine learning in the next break.
Sure.
Have a great day, everyone. Salam alaikum.
You too. You too, Mr. Alaikum assalam.
Okay. Salam alaikum.